Let's see if you can solve this Amazon and Facebook and Microsoft and Google question. So we are given the head of a linked list. We have to remove nth node from the end of the list and return the head itself. So if you want to try, you can take a pause now, else we can start to look at the solution. So in this case, we are given a k is equal to 2. So we have to remove the second node from the end. So this is -1, -2, -3, -4, -5. So if you start normal indexing, it will be 0, 1, 2, 3. Oh. So when you say remove the second element from the end, you are referring to the -2 index. That is -1, -2. Whoever has used Python will know how the indexing works when you start with the negative numbers. So for time being, we have to remove the fourth element and we have to return the head such that there is no fourth element. So how could we do that? So one of the approaches would be to use the brute force, that is count n number of elements, whatever the number of total, whatever the length of the linked list total is, and then go till n minus k, and then stop there, remove that element. That works, but there is an efficient way to do it, and that is to use two pointers. If you haven't seen my previous video, I will link it in the iCard and in the description. Do watch it so you will know what the two pointer method is. So we could use a slow pointer and a fast pointer. So what the fast pointer would do is, we will begin the fast pointer and we will make it to run from 0 to k, and the slow pointer will still be pointing at head. So when we are starting to iterate the loop, fast will be at position k, at index k, and slow will be at head itself. You can consider it to be 0. In a array notation, it would be something like a 0. So when we move to the last element k to nth location, that is last location or size in the terms of array, slow pointer will have only moved n minus k positions. So doesn't it fulfill our objective to move nth node from kth node from the end? It does fulfill our objective. Here n I am referring to as the size of the linked list, as in the total number of nodes. So we will reach the kth element. So let's look at the example again. It is second element from the end. So we will start the fast pointer, we will keep it at head initially, we will keep the slow pointer there itself, we will keep moving the head pointer k times. So 1, 2, this is where the fast will start. Let us look at it properly. So initially fast will be here, we will make it to move k times, so it is 2 in this case, so 1, 2. So fast will start from here, and then slow will be starting from head. So each time fast moves by one step, slow also will move by one step. So fast comes here, slow comes here. fast comes here, slow comes here. Fast comes to null. This is null because it is the end of the list. Fast moves here, slow comes here. So you can see that we have reached the goal node, that is 4. But our objective here is to not reach or return the nth node or the kth node from the end. Our objective is to delete this node and return the head itself. So in such a case, reaching here would not be as beneficial as reaching here. And remember, this is not a doubly linked list that we can go one step behind. It's not possible. In such a case, what we would usually do is we would start with a dummy node. So that we have an offset of 1. We are one step behind. So slow would reach here. So what we could do is slow is equal to slow's next. So what we are doing is we are removing this link, we are letting it point here, and then what we could do is we could just omit it out of the linked list. It is omitted. Done. There is no 4 in this linked list anymore. And then we will just return this original head again. So I hope you understood this approach. Now let us look at its code. So this is the C++ code for the same. If initially there is no head, we'll just return null pointer. It means that there is nothing to remove. If not, we will make a dummy node. As I explained, we'll make an extra dummy node which will help us to get an offset by 1. Then we'll make a slow pointer and a fast pointer. Initially we will run the fast pointer n times because we want the nth node from the end. And then while fast's next exists, we will keep moving it. So after this is executed, this for loop is executed. As you can see, fast will be nth index, if you would, in the terms of array, and slow will be at 0th index. So when this moves to the length of the array, fast will move L minus n, the length of the array minus n times it will move, and slow will also move L minus n times. But we will already keep an offset of 1, so that ways we can have an offset of 1 behind the nth node from the end. And then we will make slow is equal to slow's next. So there was 4 here. If you remember, it was this way. But when we have reached here, this is the node that we want to delete. What we will do is slow is here. So slow's next slow will point to slow's next. So in this way we can delete this entirely and we can achieve our objective. So while fast's next exists, fast will keep moving. So it starts from nth index from starting, and it will move length minus n nodes and slow will also move length minus n nodes, but we already introduced an offset of 1, so it will be one step behind the nth node. That is what we require to delete this node. So when we are here, there's a dummy node here, and it will move L minus length, total length of the length means the number of nodes in the linked list, minus n. It will come here instead of reaching here because of the offset that we introduced. We'll reach here, we'll do slow is equal to slows next. Slow is pointing at 3, so slows next will be slows next. And optionally we could also delete this node totally, or we could just leave it because it is not a part of the linked list. It is already considered deleted. If you want to save memory, maybe this is a good idea. And then we'll just return the original head, or we could return the dummy nodes next. That will also do the job. If you did like the video, do share and subscribe. Thank you.